All right. So let's continue with our related rate problems. Now we're going to look at questions involving right-angled triangles. Two cars leave the same location at the same time. One travels due east this way at 60 kilometers per hour, and one travels due north at 45 kilometers per hour. And 2 hours later, so exactly 2 hours later, this green triangle, one of them would have gone 90 kilometers. One of them would have gone 120 kilometers. They would have been a squared plus b squared equals c squared, 150 kilometers apart. How fast are they separating at that moment? I actually did 3, 4, 5 triangle and recognized it was just proportionate. But if you would like it to sound better, yes, 90 squared plus 120 squared. It's not that hard. Square root of that. But it's going to be 8,100 plus 14,400 is going to equal 22,500. Square root of that's 150. So no problem. Okay. So what we have in a right-angled triangle question is we have an x value, a y value, and we can call this hypotenuse a z value. And there's a relationship between the three. And all of them are a function of time. X is a function of time, y is a function of time, and z is a function of time. Now, we want to find out dz dt. We know dy dt is 45, and we know that dx dt is 60 kilometers per hour. And at the time equals 2 hours, we know that x is 120, y is equal to 90, and z is equal to 150. Now, if we want to do this with calculus, we have a relationship between x, y, and z. If we have a right-angled triangle, we know that x squared plus y squared equals z squared. And we can take the derivative with respect to time of this, since each of those values is a function of time. So how do we find that derivative? Well, derivative of x squared would be 2x, and because it's implicit differentiation, we'd have dx dt plus 2y dy dt plus equals 2z dz dt. And at this moment, you know each of the things. You know that x is, at 2 hours, 120. dx dt was 45. Y was 90. dy dt was 45. Oh, I got these mixed up. This one was 60 and this one was 45, right? Yes. Equals 2, and z is at 120, and we want to find dz dt. 150. Man, yes. But I can't copy down numbers. That's a challenge. And so if you do all of this math, well, it's not too crazy. What do you get? 75. Or you can do what Michael's suggesting is, if you notice that these speeds are constant, this is constant, so you could just do a squared plus b squared equals c squared here. Yeah. It feels like sometimes in triangle questions that there are shortcuts for these. But it's nice to see that the algebra and the related rates with the formula works as well. Eric's looking and he's going, perfect, I'm going to use the shortcut every single time and not learn how to do it the other way at all. Okay? Another triangle question. Oh, but related rate questions. Here we go. This is the same one. We're going to skip this one. This one, let's do this one. A 20-foot ladder leans against a house. Okay? Find the rate at which the top of the ladder is moving downwards. This is a scary moment in life. Right? Here we have the building. Here we have the ladder, which happens to be 20 feet. And you start climbing the ladder, and as you're climbing the ladder, you realize it's sliding down the house. And this is not going to end well. And so, at the moment, it is 12 feet away from the house. So we're finding out this specific moment when this is 12 and this is 20. How fast is it moving downward? Well, let's get some variables here. We have this we can call x. This we can call y. And x is a function of time, and y is a function of time. Z is constant. It's always 20. Okay? So at the exact moment that it's 12, you decide, I should really do the calculus here to figure out how fast it's falling. Could just use trigonometry. We'll see. Okay? So what do we have in this situation? We know dx dt. It is moving away at a rate of 2 feet per second. That 2 feet per second, it's important here that it's positive. Does that make sense? Because x is getting larger. We want to find dy dt. We should get this answer to be negative. And we want to find it at x equals 12. Well, at x equals 12, do you recognize that as your 3, 4, 5 triangle? Okay, what side will this be? 16. 3, 4, 5 proportions. So at x equals 12 and y equals 16, z will always be 20. So what equation do we have in this situation? Well, if we look at our original diagram, we have x squared plus y squared equals 20 squared. And this time when you take the derivative with respect to time, there's no z involved because it's always constant, and you get 2x dx dt plus 2y dy dt equals 0. Plugging in everything we know that x is 12, dx dt is 2, y is 16, and we want to find dy dt. Moving this number over, we'll have 32 dy dt equals negative 48. And so dy dt is equal to negative 3/2 feet per second. So a little bit different because one of the values here was constant. I'll put this in the same video as triangle questions and angle. This one, a very fun related rates question. In fact, You will not go through, I think, any course anywhere without having one question that involves a shadow. Shadows seem to just, people love being in related rate questions with shadows. And you walk and your shadow changes and you're like, oh, that's so cool, I want to figure out math. So, there's a spotlight on the ground. Let's draw it. Here it is. Oh, that looks pretty. There's a spotlight on the ground, shining on a wall 10 meters away. 10 meters, there's a wall. A man 2 meters tall, Mr. 2 meter, is walking from the spotlight towards the wall at a speed of 1.2 meters per second. So right now, there's a big shadow of him on the wall. And that's exactly how shadows look, right? Exactly scary, just like that. Does it make sense that as he walks towards the wall, his shadow is getting smaller? Okay? And if he watches it, it'll eventually be exactly his height, and then he'll get knocked out. Okay? If he's not careful. It's like, ooh, if he's mesmerized by his own shadow as he's walking, he'll walk right into that wall. So we need to set up things here. What things are changing? Okay? The shadow's height is changing. I'll call that y. The man is walking towards the wall. We need to call something changing along here. I can call this x, making this part 10 minus x, because it would add up to 10. But then x is changing. Some people answer this question by making this x, and the other part 10 minus x. I liked making the part that I made x, because if we think about what's happening, we know that x is a function of time and y is a function of time. We know that he's walking 1.2 meters per second towards the wall. Does that make sense that my dx dt would be 1.2, and it would be positive because x is getting bigger? We need to solve for dy dt, and the answer we get should be negative because it's going down. So now we've set up, and when do we want to find this? At 3 meters from the wall. When he's 3 meters from the wall, then x would be 7. So now we have the setup, and again, I said often the hardest part of these questions is coming up with the equation. How do we relate y to x? Triangles and, oh, maybe similar triangles, since this happens to fall under the category of similar triangle problems. You would, though, when you get this question on a quiz or a test, have to discern that for yourself, that this is a question where I can use similar triangles. And how do we have similar triangles? Well, in my original picture, there's a triangle here, and it is similar. And the definition of similar triangles are that all the angles are the same. They're just bigger or smaller. And in similar triangles, everything is proportionate. So, for example, if I take in the green triangle, and I need to use x, and the only other measurement I have is 2, then this proportion in my green triangle, 2 over x, has to be the same proportion in my blue triangle. And in my blue triangle, that would be y over 10. Now you have your equation. You may want to play around with this before you take the derivative with respect to time. Personally, in this one, I would probably rewrite this. So I'm going to take the derivative with respect to time, but I'm going to write this side as 2x to the minus 1, and this side as 1/10 of y. I feel then I could take the derivative of each side a little bit easier. On the left-hand side, -1 would come out in front. Subtract 1 from the exponent. Chain rule, implicit differentiation, dx dt. Equals, derivative of 1/10 y would just be 1/10 dy dt. We know that dx dt was 1.2. Are you okay if I change that to a fraction? -2. I'm going to change the x squared to be on the bottom. X is 7, so that would be 49 on the bottom. dx dt was 1.2. That's 6/5 equals 1/10 dy dt. Multiply both sides by 10 and do a little bit of simplifying. What were our units? Meters per second, thank you. You could have, yes. So you could multiply both sides by 10 and have 20x to the minus 1. Perfectly fine. I like that actually a lot. So you can fiddle around with your equation before you take the derivative, because if you have an equation, that's what an equation is. One side is equal to another, and you can manipulate those. Yeah, I really like that a lot. Right? I like that a lot. That would be, it comes out to exactly the same. It's just when you multiply by your 10, but that even looks nicer. So you're allowed to do that manipulation beforehand to create something that is nice. Now, is this the last example that you have? Okay. I have some more examples. Oh, and Alan is like almost doing cartwheels here. He's so excited. Television camera is positioned 4,000 feet from the base of a rocket launching pad. Rocket rises vertically, and its speed is 600 feet per second when it has risen 3,000 feet. Okay, so what do we have here? We've got camera. Right? It's a beautiful picture of a camera there. Oh, it actually, that's a camera. Oh, can you not, a little bit of imagination, I really see an older handheld camera with a, yeah, yeah. How do you make one of those NFTs? Can I just like take a screenshot and sell this online or something? This could. I can just retire. This is, all right. Well, hope you enjoy learning the rest of this on your own. Put that up for sale. Okay, there's our camera. And there's our rocket. which should probably be smaller because I'm going to make a dot up here that says that's 3,000 feet. Otherwise, it's just the longest, skinniest rocket you can ever imagine. Okay. And this was on the ground, so we'll move that down so it measures up perfectly. Okay. What do we know? We know that this is 4,000 away. We know that y is changing with respect to time. How fast is the distance from the rocket? So we're wanting to find this. And we know that z is a function of time, y is a function of time. We want to find dz dt at y equals 3,000. And can you see it's just 3, 4, 5 again? They're not being very creative with their triangles. They meaning, I guess, me, because I put these questions together. Anyways, at y equals 3,000, z will be 5,000. And this question, we've already done one like this before. We want to find, we know that dy dt is changing at 600 feet per second. And it's just a matter of a squared. And the 4,000 is always the same. The y is changing. The z is changing. Take the derivative with respect to time. And we get 2y dy dt equals 2z dz dt and my mental math is right. It's 360 feet per second. Is that right? Feels a little bit funny. No, nobody's going to check. We should just do it. You got 360? All right. Perfect. I guess initially you always think of your hypotenuse as the longest. So initially I imagined that being faster, but I can see that speed being slower because it's, yeah. This is part here, part A is a right angle question. But it's part B why this question is listed. If the television camera is always kept focused on the rocket, then the camera has to rotate as the rocket goes up. Okay? So that introduces an angle right here that's changing. And theta is a function of time as well. How fast is that camera's elevation changing at that same moment? So now we need to create an equation that involves theta. And what do we know? Y. Y is changing. And we know that x is 4,000 all the time. Could you create a relationship between theta, y, and anything else in this? Yes. We could just say that tan of theta is equal to y over 4,000. And then we could take the derivative with respect to time of this. What's the derivative of tan? secant squared. So you would get secant squared theta times d theta dt, because it's equals 1 over 4,000 dy dt. When y is 3,000, okay, right? What are we trying to find? We want d theta dt when y is equal to 3,000. And the problem here is you don't know what theta is. Could you solve for theta in that moment? Yes. You could also solve for cos of theta at that moment. And I'm going to do it that way because it doesn't involve a calculator. If I want to find theta when this is 3,000, I'm going to have to do tan inverse of 3,000 over 4,000. And I'm going to go to my calculator and I'm going to get some sort of decimal. If I don't want to find out what that decimal is, can you see when y is 3,000, z would be 5,000, that cos of theta would be adjacent over hypotenuse, 4,000 over 5,000, which is 4/5. And then secant of theta would be 5/4. So plugging things into my equation, secant squared theta will be 25 over 16 d theta dt. dy dt we already knew to be 600. Wow. I really chose a really good space to do this question in. Solving for this, this will be 60 over 40. Moving things to the other side, so d theta dt, 6 over 40 multiplied by 16 over 25. Mental math, this simplifies to 4 and 10. Kind of not the nicest number. You could do 12 over 125, right? Mm-hmm. Without your calculator? I'd probably give you smaller numbers. It wasn't so bad. Yeah, and again, I'm not going to take off marks if you don't simplify a fraction in the end. But 12 over 25, and here's something that we've never really fully talked about, but when we go to our units, time here was measured in seconds. This is radians per second. Calculus, all of our nice derivatives for sine, cos, and tan are only nice in radians. No, I didn't tell you that. Look at that. You learned something. Well, you've been learning lots of stuff new in calculus probably every day, but there's something else new in calculus. That, because one time while I was doing these questions, I don't know when it was, as a student or whatever, I was like, what should I put in my units? Should it be radians or should it be degrees? Or does it not matter? And then it was like, well, that's totally different answers if you have one in radians or one in degrees. So all of our calculus with trig functions, we never talked about it, but it has always been with radians. So good? Yeah, there's one on the back. Oh, did I get the same answer? 0.96, is it 0.96? I'm sure it is. 96 over, yeah, then that's 0.096. Yeah, 96 over 1,000 is actually nicer for changing to a decimal than 12 1/25ths. A kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. So we draw our string. Here's our little guy. He's got a string, having a good day. Here is our kite. Draw it mathematically correct. Definitely to scale. That is one huge kite. Okay. And it's 100 feet above the ground. So we know this is set at 100 feet. Apparently that is staying constant. This guy's really good at letting out the string. We've got an angle between the string and the horizontal. That would be this angle right there. And we want to find out how fast the rate is between the angle, the string, and the horizontal is changing at the exact moment that he or she has let out 200 feet of string. So what do we know? We know that theta is a function of time. We know that x is a function of time. Yes?
I know it's never specified, but it is assumed. Which direction is it moving? It's assuming that it's moving outwards, but it could be moving inwards at 8 feet.
It could be.
We don't know.
No. Now, generally, what happens with a kite, it's a good point, but I have very rarely seen someone who has a kite out in that direction being able just to reel it in easily because it's coming back towards them. You know how hard that is? You first have to let your kite out. Then you have to run faster than wind goes while letting your string go loose so that you're on the other side of it so now the wind is pushing into it so that you could roll it in. I don't think that's very likely.
I'm just saying, it never specifies.
So.
Okay.
There's the cloud.
Pull the string in. You're pulling the string in right now. The person pulls the string in. Which way does it go? It goes towards them.
Okay.
200 pounds let out. Doesn't mean you're not bringing it in. No, it doesn't. Normally, I bring my kites back in.
I think you technically have to specify what a normal kite logic would be because some of us have not flown a kite
I
in
never learned
years.
kite logic in school.
There we go. So there we go. Just moving forward, if you're writing a quiz or a test and you're making an assumption, you can just assume that that's wrong. No, it's just wrong. Oh, great. Unless that assumption was to look over and copy Alice's work, then you can assume that you were right. Okay, so we want to find d theta dt.
Alice used my logic.
No, that's because I drew it wrong the first time. I didn't bother to erase it.
So what do we know that it is moving horizontally at 8 feet per second, and this would be positive because he's letting string out.
No.
if you were bringing it in, then more than 200 would have been let out.
200 have been let out, doesn't mean you're not bringing
Okay.
it in.
Again, I'll refer to this. Anyways, we have 8 feet per second for dx dt. We want to find when z equals 200, and we don't have our nice triangle here anymore. What do we get for our other value here? Root 3 times 100? I think so. So x, or I'd write that as 100 root 3. A squared plus b squared equals c squared. Yeah, I think that works. Well, it does matter because it tells us what x is. Maybe it doesn't, okay? Because what we could do here when we're setting up our equation, right, what do we need? We have, is there a relationship between theta and the 200 and, or the z, because the z is changing. So we can also put on here that z is a function of time. And we'd have dz dt, but we don't know what dz dt is. So we do need to use x, because we've got a dx dt. So then I would set up my equation with tan of theta again is 100 over x. Take the derivative with respect to time of this. Angle questions often have tan, so you get secant squared theta times d theta dt equals, I would think of that x as an x to the minus 1. And we would have secant squared theta d theta dt negative 100 x to the negative 2. So that x does come into play here. Okay, can we do this without a calculator? Yes. So we figured out this to be 100 root 3. So can you see that cos of theta is 100 root 3 over 2? So that would mean that secant of theta would be 2 over root 3. Two over root 3 squared will be 4/3 d theta dt equals negative 100. X is 100 root 3. So this will be 100 root 3 squared, which will be 100 times 100 times 3. Can you see why I might have written that as 100 times 100 instead of 10,000? So I can cancel them out. Some beautiful. And we know that dx dt is 8. So yes, this 100 will nicely cancel out with that 100. Multiply both sides. By 3/4. Oh, that cancels out. And d theta dt will equal negative 1/50. What are our units? Radians per second. Thank you. Very cool. So, like I said, related rates, and we're going to spend, I've got a handout for those of you that do not do as well with opening textbooks. Yes, you can carry this. Look, how long would it take you to complete this? There's only 50 related rate questions. Right? Right? So, after every related rate question you do, you decrease the time per question by 10 seconds. So your rate of change is how fast are you completing the assignment at question 27? No, we're not turning it into related. And the answers are on the back, which is really nice because you can get a sense if you're getting these or not. What I would suggest is try to not do two of the same kind of question in a row. Like don't do liquid in a shape problem, liquid in a shape problem, or shadow, 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 shadow problem, right? So, and as you go along, if you're like, ooh, I think I'm pretty good at the similar triangle ones, I'm going to skip this one and move on to another one. That is perfectly fine. So, for Monday, when I am not here, you can work on this, because this is sort of like the main review for related rates. I also have a pretest for the rest of the unit, which you can use to study from. And I gave one to you already. Yeah. I am still recording. I should probably stop that soon. Right? But we should, what we should really make sure that we do is the picture of that camera should be the original, because when a video comes up, they always start with one picture. And I'm sure if that camera picture was on there, the views would be like, ooh. Yeah.